Okay, the recording and the transcription have now started. So if you don't want to be recorded, just don't come on the video. Okay, so as I said, today is about I/O systems. All of those different things that we've got hanging off of our machines that perhaps might have different functionality, might have different ways to connect, might have all sorts of different things. Clearly, we don't want to think about it. We don't want to worry about whether, I don't know, we don't want to worry about whether our mouse is connected with a USB cable or a Bluetooth. We don't want to care about whether our screen is connected with a VGA cable, an HDMI cable, or a DisplayPort interface. We just don't care, nor should we have to. So the operating system, as ever, is going to step in and save us from all of that kind of stuff. So what we're doing today is talking about what we have to have in place for that to happen. I suddenly realised how drafty it was and I couldn't figure out why. Normally I have to close the door because the family are all in, but there's nobody in today, so I'm only in danger of being attacked by cats today. And it's nice weather, so that's unlikely. So the operating system is going to dive in and help us to connect to our I/O systems, no matter what they are, no matter how they're connected, no matter what kind of interface they have. So we're going to have to look at all those types of things, the interfaces, subsystems, all that kind of thing, and try and figure out how that fits in to the rest of our operating systems. Because clearly, we can't really have a computer without an input-output system. I mean, to be fair, some computers might not have an input. You might have a computer running. I know, actually, I can't think of a computer without an input. Anybody want to give me an example of a computer without an input? I don't think of one without an output either. And it may be the stuff that we're used to: keyboards, mice, screens, disks, storage, USB. Or it might be stuff that we're not thinking about: connections to other computers, connections to hardware. Because we've got all these devices, we're going to have some way of interfacing them with the operating system. And we've spoken about device drivers before. So what the device driver does is allows a new system. Maybe you had a printer that was black and white inkjet, and now you've moved on to a printer that's a color laser. Now you don't have to do anything with your in how you think about printing. You don't have to suddenly think, oh, do I have to change my typefaces? Do I have to install a new set of fonts? Do I need to make some change to how I'm creating my documents? All you say is, nah, print it to this printer now, please. Device drivers are the things that allow us to do that, and they will translate from how we're looking at a document to how the printer looks at its document. And the same will apply for every other device. It won't matter if it's serial or parallel, how it's connected. The device driver will take care of that for us. And a device driver is quite a powerful thing. I find it hard to imagine that there's anybody in this lecture, for example, who hasn't had to install a new device driver on their computer, either because they've installed some new hardware or because the device driver's outdated and you've updated it. But as you know, if you install something, put in a new printer, add a new mouse, you very often have to put in a new device driver. So it's a powerful way of allowing us to extend our operating system. Because of course, clearly it would be impractical. You might just be able to install in your operating system software that would cope with every known piece of hardware in the world right now. But what you absolutely can't do, even if that were possible, and I'm not convinced that it is, what you absolutely can't do is ship an operating system that will cope with every piece of hardware that's in the world come tomorrow. So device drivers allow us to extend our operating system without reinstalling our operating system. And they allow us to do that for all the different hardware types that we have and all the different functions that they have, whether it's display or sending information or storage or whatever it happens to be. That said, there are some things that are common. So there's the port. How do you actually connect to this device? A bus. How are the devices connected to all the other pieces of hardware on your system, like the CPU and memory and all that kind of stuff? And possibly how are the I/O devices connected together? So how, for example, do you send a file from a hard disk down a TCP/IP network connection? And we'll have a controller. So that's a physical thing, electronics that understand what your device actually is, how it needs to connect, and all that kind of electrical engineering stuff that physically allows us to connect a monitor that's connected to a 220 volt connection running on AC to a computer that's running in 5 volt DC. Somewhere in there is going to be electronics. And that's what the controller is. Having got all those things in place, you end up with something like this. So our bus is the main interconnector. It's just a road where all the data goes. And we connect all our I/O and into this bus. So our graphics controller will send information to our monitor. Information that's been sent from the screen. So when you're looking at the screen right now, the application's updated the screen. That has to then be sent down the bus to the graphics controller to be displayed in your monitor. And every time I move that mouse, the same thing's happening. Your monitor's updating. Processor is taking note that the mouse has moved, updated the screen, updated the memory dump of the bitmap for the display, sent it out into the bus, swapped its way along into the controller and into your monitor. But a touch faster than the way I've just described it. And everything else connects the same way. Although sometimes you might have more than one device connected to a single controller. The IDE controller will let you connect 4 disks, for example. If you have a USB connector, you can have 8, 16 USB devices. I can't remember. SCSI controllers allow you to have another SCSI bus that you can hang things off of, disks and graphics tablets and all that kind of stuff. So it starts to become quite a complicated thing. And one of the things I want you to take note of is this PCI bus. Our I/O bus there's taking a big hit. Every time we do anything, there's data going down there. And if the data is going from memory to update our graphics controller, it can't be going from memory to save our file. And you saw that earlier because my memory was full of stuff. programs were being loaded from the hard disk into memory, they were being running, they were updating, they were being saved back into the disk after the update was completed. Every time that happens, the PCI bus is taken, and there's only one bit of data can be on that PCI bus at the time. So my processor couldn't update my monitor, and you couldn't get your weekly hit of music. So I had to wait for this to settle down before I could do these other things. It also didn't help that the processor was completely swamped. Okay, so we've got all these devices, all connected, all moderately stupid in that the controllers will take information and will do with it what they've been told. But it's still all controlled by the processor. And the processor will send out instructions to the I/O devices. So you install the driver, and the driver says something like, if you want to print a P on the screen, send the binary string 01100101 down the I/O data line, and send the command 000101 down the down the command bus. And I'll put a P on the top left of your monitor. If you want a P in the top left of the printer, it's probably the same data, but a different command. Sorry, Connor, I can see your lips moving. I'm not sure if you're... No, talk to somebody else.
Yep, apologies.
No, you're fine. I wasn't sure if you're trying to talk to me. I didn't realize you were talking to somebody else. So there'll be commands, addresses, data to write. All that stuff will have to be sent out to your I/O device. And we actually have specific registers where that will happen. So the CPU will place these commands, the data, all that kind of stuff into the registers, and that will then be sent out to your I/O devices. Often that's done by integrating the devices into our system by mapping memory. So we've got two choices. We can either send direct instructions. We can recognize that we have a device connected to our system, and we can send it specific instructions sent specifically to that particular device. Often though, what we do is say, well, hang on, we've got all these devices. Why don't we integrate it even further? Rather than having a whole set of instructions for the SCSI controller and a whole set of instructions for the IDE controller and a whole set of instructions for the graphics controller, why don't we just pretend it's memory? And that the SCSI controller is at memory location 20,000, and that the IDE disk controller is at location 21,000, and the graphics controller is at location 30,000. Clearly, they're probably going to be well clear of normal memory. Not always. Sometimes you actually want them to overlap for reasons that we'll come to. But what it means is you can use the same instructions. As long as you can send out an instruction to memory, if we memory map the I/O, we can use the same idea. We send out an instruction to memory, and think back of your little man computer. What would happen if after the end of those 100 post boxes, there was a printer at 101? So when you sent out an instruction to memory address 101, it fell off the end of memory and actually went to the printer. So it's actually quite an easy way of extending our system. And that's called memory mapped I/O. All the devices have addresses, and we simply send information to that address. That can be really helpful for things like graphics. So I've got a screen here, and this screen is built up on a set of bytes. or possibly a set of words given the type of screen I have, in that a byte wouldn't be enough to encapsulate the colour information. But we'll call it a byte just for ease of. So we've got a set of pixels on the screen, horizontally and vertically. Or excuse me a moment. I did say there was no one in the house, which means that someone, of course, had to come to the door. Excuse me a second.
Right, Connor, teach us the next slide.
Look at that, it vanished. Wow.
Sorry about that. So yeah, we have a display made up of pixels. The pixel is, for sake of argument, a byte, saying which colour we have. So we have a whole bunch of bytes saying black, 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 blue, 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 white, 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 black, 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 and so on, all the way down. Do you know what would be quite nice? What if we replicated that in memory? Then whenever we updated, so when that mouse moves over, we update from a white to a yellow. And then we just blast that whole pile of memory down from here along the bus into a monitor. And if we have a fast enough refresh rate, it means that we can update our screen really quickly. Particularly help. We don't have to do it that way, of course. We don't have to keep it in memory. We could actually have the graphics controller be a graphics card, and we can update memory in there. So rather than update memory here and then blast it down as one block, we could actually update it and send it down as updates. And you can have a think for yourself what that will do in terms of speeds. Either way, we can memory map the I/O, and we would do the same thing for a printer or a storage device as we would do for graphics. That is so helpful that all the Windows machines that you guys are using use that just now. And in fact, the I/O addresses have become standardized. So we have things like DMA controllers and interrupt controllers and game controllers, and you know, all those serial ports that you have in your system. And your diskette drive controller, because I'm sure that you all have that right next to your SSD. All of these controllers are mapped to an address range, and to interact with these, we simply send a message to that address. Okay, everyone happy with that before we move on? Okay, so we can send and receive data from each of our I/O devices. How do we know? I'm moving my mouse. How do we know that this I/O device, my mouse, is creating a signal that says up? Well, we've got a couple of ways of doing it. So one way is we're in a lab together, and I wander around the lab, and I go up and down the rows saying, Matthew, need some help? Lisa, do you need some help? Kerr, do you need some help? Calvin, do you need some help? David, do you need some help? Ali, do you need some help? Zara, do you need some help? Aaron, do you need some help? And I work my way through the lab saying, do you need some help? We can do the same thing with I/O devices. Mouse, do you have anything to say? Keyboard, do you have anything to say? Disk, do you have anything to say? That's called polling. We go around each device, look at what a flag, it's a busy bit that says, are we doing something? And if it is, then we do whatever's required for that I/O. While it's doing that, of course, it can't do anything else, nor can it take note of any other I/O, which might be okay or it might not. So say, for example, it was a printer, and the printer saying, oh, I can take some data, please. And you have to send out all of the information for a color laser printer for just one page. And you think about how much data that is, and you think about how much time that takes to go down the bus and the amount of time it takes to get it all into the printer. While you're doing that, you can't be doing anything else. You can't be checking to see whether the mouse is moving. That might be okay, because all will happen is rather than having a smooth movement of the mouse, you end up with jaggy mouse. You move it and eventually it ends up somewhere, and probably you've seen that actually when I/O slows down. That's okay if it's a mouse or a keyboard, because both of those have hardware in them. They have buffers that say up, 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 up. And then when it finally takes notice, it transfers all those ups, or it transfers the last 64 keystrokes that you had all in one bus. And again, you'll probably have seen that. You'll be typing away, nothing happens, screen's not updated. You think it's missed it. You start typing the same thing, and then your name appears 6 times. So what's happening there is it's busy doing other I/O. And as I say, that's okay for a mouse or a keyboard. It's not okay if you've got a network connection. What's going to happen to a packet that's sent over a network and you don't deal with? Answer? Disappears. Goodbye. If you're lucky, it might send back a message saying that one wasn't received. Can you send it again? But it just depends. And again, you'll have seen that. Anybody who's watched online TV will have seen that happen. All of a sudden, the screen goes weird because it doesn't have enough data coming in to update the screen, or the sound goes off, or whatever it happens to be. So polling means that you go around everybody and everybody gets some time, but you have to wait. And of course, going back to my example about the lab, the answer from most people is no. It's the same with the computer. The answer from most devices is no. I'm not using my keyboard just now. I'm not using my disk just now. I'm not using that camera. Not this camera, that camera. I was not sending anything. I'm using this microphone. I'm not using that microphone. That USB connection isn't doing anything. So we're spending all this time saying, do you want to do anything? And they're going, no. Are you sure you don't want to do anything? No. Are you sure you don't want to do anything? Go away and leave me alone. Maybe it's not the best way to do it. Maybe we should do it the other way. Rather than me wandering about the lab saying, do you need any help? I'll wait until somebody goes, can you help me? And for a computer, that's an interrupt. The computer generates an electronic signal down an interrupt line saying, hello, I'm here, please help. So I move the mouse, it sends an interrupt. The interrupt says, oh, I've been interrupted. What's happening? And it looks at the bus and it recognizes the device number for my mouse. So it says What do you need to do? Oh, I need to transfer some information. Fine, it goes, it transfers the information and it saves it. So the interrupt request line is triggered. The interrupt handler receives the interrupt and does something with it. Now we have multiple interrupt handlers because we have different types of device. My mouse is sending up, 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 left, 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 left. My keyboard's sending QWERTY. My hard disk is sending a pile of binary data. So we have different handlers to do different things. Now, just to be clear, the handler is probably not acting on that interrupt, which is to say it's interrupted, it's received a message for up. It may not actually act on that message. And again, that's why you see your the mouse sort of jumping or the data on the screen updating in a chunk. It takes the data, it saves it somewhere in a buffer, but it might not act on it depending on what it's doing elsewhere. So this is about getting the stuff in and making sure we don't lose it. Sometimes you can't even do that. So we decide whether or not interrupts are maskable. In other words, we might set a priority in the same ways we have in other areas of the operating system to say, well, actually, if we're doing this, we probably don't want to do this. Do we really want to lose data that's coming in over our network connection for a mouse movement? And the answer is probably no. So we'll do the interrupt first. So they have a priority as well. So we'll set up priorities. If more than one device interrupts at the same time, we'll work based on that priority. But some devices are what we call non-maskable. In other words, we'll do them no matter what. And it's up to the operating system to decide which devices shouldn't be maskable. So what we end up is this. We have a CPU busy churning away. At the same time, we have an I/O controller. The CPU says, hello, please send me some data. And for example, your disk controller says, oh, okay, hang on, I'm going to go get some data. It goes and grabs it off the disk. Oh, the disk's spun and the head's gone in and out. And that takes a wee bit of time. While it's doing that, the CPU can just get on with things. There's no point in the CPU stopping while the hard disk spins. So the CPU keeps going. Meantime, the I/O controller goes and gets its data. And when it's ready, it generates that interrupt. And it says, hello, data here. CPU gets it, says, all right, okay, I'm going to stop my PowerPoint presentation now. I'm going to transfer control to my interrupt handler. In other words, I'm going to go get the information from the I/O controller and save it somewhere. Once it's got that data, not processed the data, just got the data, it will just go back to what it was doing before. And that will be in the same cycle of processes that we've looked at before. And whatever this data was, it will get used when the process that needs it comes back into line. So quite often this initiates I/O will actually put the process that does that into the wait state, because it's waiting in I/O, and we said that back when we did process scheduling. If you're waiting in I/O, why do you get CPU? Well, you wouldn't. So you initiate the I/O, process will go into wait state, it'll do some other processes, chug, 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 chug. When the data comes in, it gets saved, CPU keeps going in its same way, and then eventually the process that asked for the I/O will come back online and can start using that data. Sometimes the CPU won't initiate the I/O. Sometimes it'll be data that's coming in, but the same thing will happen. It will create an interrupt. The CPU will receive an interrupt and the interrupt handler. So my process just now isn't initiating I/O with my mouse. Instead, my mouse is initiating the I/O because I'm moving it. So it moves, it says down, creates an interrupt, says to the CPU, we've got some data from this I/O device. The CPU stops, takes in the down, saves it, and goes back to what it was doing before. Everyone happy with that? And as with I/O memory, there's a set of vectors for interrupts. And again, this is a priority list for certain things that we want to pause and interrupt for. And you can see that the first 32 of them are for the CPU itself, general protection fault, page fault, and you all know what a page fault is. Segment not present, you all know what that is now. And then from 32 to 255, these are the other interrupts. So we can start adding things in. So as you see here, interrupts aren't just used for I/O, they're used for exceptions. Stack fault, page fault, segment fault, double fault, which I thought was tennis, but what do I know? See, in a class that would get a laugh, and I've got no idea if it got a laugh or not. Terrible. So we'll use the same sort of interrupt mechanism for other things like problems. But the same sort of thing will happen. You'll get an interrupt, it'll pause, it will do whatever it needs to do to sort itself out, and it'll go back to what it was doing. And just like other systems, if you have a multi-CPU system, then an interrupt is just a process like anything else. The interrupt handler is just a process like anything else. So if you've got more than one CPU, you can do more than one interrupt. Okay. So there's no questions. I want to talk about this now. One PCI bus. One place where all the data from all the devices and all the hardware gets sent from one to the other. Sometimes that might not be a problem. Keyboard, I press a key, 1 byte of data goes over the bus and goes into memory. Yeah, 1 byte, that's okay. But what if you open a file? What if you open a 100 megabyte Word file? What if you open a 4 gigabyte video file? So it's on the disk, it has to go into the bus and it has to get into memory. And while those 4 gigabytes are transferring into memory, you can't do anything else. None of these devices can get access to the memory while that's happening. It can get access to the bus while that transfer to memory is happening. Think of it like the high street in a village. Every so often, a bike will go down. That's fine. Bike will go down and get out of the way. Sometimes a car will go down, and it's not a big bus, it's not a big road, so the car will take a lot of space, but it's not going to be there for long and it'll get out of the way. Sometimes a tractor comes along, and it's big and slow, but predictable, and again will be out of the way. Sometimes you get a whole fleet of Arctic trucks that are nose to tail going through your road and no one else can get on it, and you get a traffic jam. And that's kind of what we can get here. You can get a traffic jam with all the data that needs to go, say, from a file on disk into memory. Well, just like what we might do with a traffic jam, we can do the same sort of thing with our I/O devices. We can build a bypass. Except it's not called a bypass, it's called direct memory access. There's always just one byte at a time going down the PCI bus, or to be precise, one word at a time, depending on the hardware in your system. So what we're bypassing isn't the bus. What we're bypassing is the processor having to control the bus. What we're bypassing is the processor saying, send me the next byte, 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 send me the next byte for 4 gigabytes. And while the CPU is controlling all that, it can't be doing anything else. So what we do is we set up DMA not to bypass the bus. We've still got a bus, but we're bypassing the CPU controlling it. So what we're doing is we're putting in extra hardware. So we've still got a disk, we've still got a memory, and we've still got the bus. But instead of the CPU saying, send me the next byte, 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 what the DMA can do is say, okay, I want 4 kilobytes of data from here to memory address 10, go. And the DMA controller will take care of the send me the next byte, send me the next byte, send me the next byte. You might not think that helps much, but the bit that it leaves out is the CPU. So while DMA is busy transferring all that data, the CPU can go on with what it's doing. It can still run its processes. Because it's still there, it's not needing to access anything, because it will have some cache. So all the stuff that it's running is already in its cache memory. So it can still run its processes with its cache. In the meantime, DMA can go on, getting the next byte, getting the next byte, getting the next byte, getting the next byte, until such point as it's got them all and it interrupts saying, yep, you're done. So we can set that up to allow us to speed up the system. It's at a cost. We need the DMA controller, that's extra hardware. The cache, well, quite often we'll have a cache anyway, but we might need to make it bigger. But the payback in terms of the CPU being able to continue on with its work while the data is transferred is quite high. Okay, I am about halfway through this presentation. We're about halfway through the time that we have. Time for a break?
Yes.
Okay, do you want 5 or 10 minutes?
I'm up for 10.
Well, Connor, ask and ye shall receive. Okay, we'll take a 10-minute break and I'll see you back here in 10 minutes to talk about character and block interfaces.
Can't wait.
I
See
know
you then.
you can't wait. See you later. Okay, and we're back. Anybody thought of any questions from the stuff that we did before the break?
There
Other
was a
than
wee.
how come it takes?
Sorry. There was a wee bit with
That's okay.
the expansion slot for the PCI. I'm just trying to like relate that to my motherboard. Is that the part that I might set, for example, like a graphics card on or a network interface card kind of thing? It makes sense in my head, but I'm definitely not saying it well.
Yeah, I'm trying to follow what you're saying. Try it again a bit more slowly.
See the wee diagram you had that showed the PCI bus? Could you bring that up again? No, not that one.
Yeah, hang on.
All right.
First thing I'll say is remember this diagram is from,
Yeah, it's pretty old.
but that said,
Aye.
what's the,
So the part on the bottom right that eventually connects to the PCI bus called the expansion bus. I've got two parts of my motherboard that are called PCIe expansion slots. I'm assuming they're related.
yeah, so they're basically to give extra speed. So the idea is you can have faster stuff, but also be backwards compatible,
Mhm.
because that's always an issue when you have new things coming in. So in ye olden days, it wasn't the PCI bus, it was the ISA bus. And when it came in, you would have a PCI bus that was connected to the ISA bus so you could use newer PCI cards, which in essence was basically faster graphics.
Right.
Now we're seeing the same thing. We'll get faster hardware, but A, you've got lots of old hardware out there, and B, you've got lots of manufacturers with lots of stock and lots of motherboards. So instead of having to say take the whole thing, chop it up and come up with a whole new set of stuff, you can add in extra bits. So eventually that will take over on the same way as PCI took over from ISA. But in the meantime, you can run both of them and have, excuse me, the benefits of that without having to throw out everything that you have, if that makes sense.
Yeah. Yep. That was the only question I had. Thank you.
Particularly actually the one you're talking about, because PCI, do you know what the E stands for in Express in PCI?
Yeah, I was actually going to say expansion, so no, I didn't anyway.
It's Express, so it is a faster. So it's basically the same PCI bus, but faster. In the same way as all sorts of things get faster. But you need some way of retrofitting them. So you can have a PCIe controller to allow you to have the fancy, fast graphics controller, say, and I imagine that's probably what yours is connected to, without having to update your IDE controller or your expansion controller. So you can get the economies of scale and all the stuff that already exists, but give yourself fancy, fast new graphics, for example. So yes, PCIe is Express, not expansion. Any other questions? Okay, so let's look at different types of interface. Because I said right at the top, we don't care in essence. We just send stuff, receive stuff. It's all just data to us. But clearly, different devices work in different ways. At its most basic, we might have devices that get characters, a keyboard, or block data. So you wouldn't get a character from a hard disk, as we saw last week. You would get a block, which is of, say, 512 or 1024 bytes. Some devices are sequential, the tape drive. Some are random access, like the disk. Some are synchronous or asynchronous or shareable or all these other things. One of the nice things is the drivers and the controllers work together to make sure that we don't care. So we can end up with something like this. We've got our operating system kernel, which has an I/O subsystem. So that's for all of the I/O. But all the different devices have their own specific drivers, which connect to the specific controllers. Now, you might just be thinking of it in terms of oh yeah, I can't plug a display port into a USB connection. But that's more of the effect than the cause, by which I mean it helps to have different connectors so that you don't mix them up. There's other things to it as well, of course. Voltage levels, amount of data, speed, all that kind of stuff. But it does help to have specific devices to do specific types of job. That said, by the time the keyboard has sent its data to the controller, and the controller has interfaced with the driver, and the driver has passed it on to the kernel subsystem, it doesn't care anymore. It's just data. Or when the disk has sent 1 kilobyte of data to its controller, which is then passed on via the device driver into the kernel's I/O subsystem, it doesn't care. It's just data. So it's part of this idea where we insulate the kernel from the day-to-day work of it. It also means, of course, that we can swap these out, we can change them, we can update them. In extreme cases, we can even update the controllers, because when you think of yourself as having a graphics card, it also includes the controller. So you can send more information for a higher resolution, or you can send it faster for a faster response rate. You know, is it going to be 50 hertz or 60 hertz or 120 hertz? What's it going to do? So you need physically different hardware for that kind of stuff. So all sorts of I/O devices have different ways of sending data. And the changes in those, the different ways that they work, are handled by these device drivers that we install. And as I say, block and character are the two main ones, but we also want to look at memory mapped and networked information. So block and character devices tend to work in the same way, in that we read or write data. And we can use that memory mapped idea that we were looking at before. So we can set up a keyboard and say it's at memory location 1, 2, 3, 4, 5. So whenever we get an interrupt from the keyboard, we go to look at memory location 1, 2, 3, 4, 5, and that's the character that the keys that you've just pressed. And you go grab it from location 1, 2, 3, 4, 5 and put it to wherever you need it. Or if you've got a printer that's at 2, 3, 4, 5, 6 and you want to print a P, you send the P out to memory location 2, 3, 4, 5, 6, and that's then taken by the device driver and sent to the printer to print your P on the screen. In terms of how they work, there are broad similarities. So you'll read a character from the keyboard, or you'll read a block from a device like a hard disk. It doesn't really matter. We also have network devices quite possibly more network devices than anything else right now, particularly if you extend network devices to include anything that's not physically connected. So traditionally we thought about network devices as something that's connected to an RJ45 or even a BNC connection. But it's not, of course. It's anything that's on Wi-Fi, anything that's on Bluetooth, any kind of network device. Because there's an extra layer to go through. It's not just the data, it's getting it from where it started. So my mouse creates some data. But that data has to then get from here to that computer. And the only way it can do that is via Bluetooth. So we have a network protocol, in this case, a Bluetooth protocol. But it could be anything. It could be TCP IP, it could be UDP, it could be whatever. Now, to handle all this, it's useful to make sure that data is all going synchronously. Actually, I'll not use the word synchronously because that has a specific meaning with data transfer. It's better that the data transfer is synchronized. You've all seen soldiers marching, and they all go. Everybody goes at the same time. And you've probably always seen a funny YouTube video where somebody gets it wrong. They're supposed to turn right and somebody turns left and walks into somebody and everybody falls over. The same thing happens in a computer system. We need that beat. And that's what that clock is. All computer systems have a clock. And everything that happens to the beat of that clock. When we talk about a CPU having a speed, that's what we're talking about. How often can it execute an instruction? Instruction, 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 instruction. And clearly, if we can make the clock go faster, we can execute more instructions. But the problem then becomes getting that synchronized. In the same way as if you try and get a bunch of soldiers to walk at a normal speed, it's easier than getting them to walk at a fast speed. A normal march is easier than a quick march. So we need all this sort of background stuff in there so that we can synchronize. Clock tick, send a request. Clock tick, initiate a transfer. Clock tick, receive a transfer. Clock tick, send interrupt that the data's ready. Clock tick, start transfer. Clock tick, still transferring. Clock tick, still transferring. Clock tick, transfer finished. All done to a regular. There are other differences in I/O types. And we said earlier that we linked it back to the idea about processes going into a wait mode. But not all I/O requires that. So where we go into a wait mode until the data is transferred, that's called blocking. So the process is suspended, and we've talked about that a lot before. But sometimes you can do I/O where it's non-blocking. You can request something and just still continue on. You might send out a request over a network connection. Doesn't mean you have to stop doing what you're doing. You can still work away because you know that that network connection is going to take time and it would be unfair. And there might be other things that you can go on with. So some I/O is blocking. You need to stop what you're doing and wait for it. Some is non-blocking. So you get asynchronous processes where we can run while the I/O is executing. And of course, that's really hard to do. It's really hard to synchronize that dance between the process going and the data coming in. So we can have either synchronous or asynchronous connections. So synchronous is what you'd expect. We request the process, it goes to the device driver, it goes to the interrupt, hardware is transferred, and then it works its way back. Asynchronous says, well, actually, no, initiate, go back to the process, and then this stuff will work its way over time in the background until eventually you send back the data. So this would, the process would wait while the transfer is done. Here, the process continues while the transfer is done. That's synchronous and asynchronous. Now, there was a diagram where we looked at all of these things here. The hardware connected to a controller, connected to a device driver, and I said about this mysterious kernel I/O subsystem that connects the drivers to the kernel. So let's look at that I/O subsystem. Because it's got a few jobs. One of the things it's got to do is analogous to processes. It's got to schedule all of the I/O requests. So you might get an I/O request from multiple processes. Word might want to open a file. Excel might want to open a file. Word might want to print, so might Excel. But you've only got one hard disk and one printer, so you're going to have to schedule the requests. And again, we're into this idea about how you do it. Do you just say, nah, we'll do it in fairness, we'll do one after the other? Some things do it, they try and take note of what it is you're trying to do. So you might, for example, be running, well, I'm running here, PowerPoint over there and Teams over there. And I've got a video running over there and PowerPoint running over there. Now, when I change my PowerPoint slide, it might implement a quality of service thing, by which I mean it will decide that updating the video over here, because you notice if videos become jerky and stop, it might say, no, I'm going to do a lot more with the video here than I am with my PowerPoint. Because you, as a user, won't notice if it takes 1/10 of a second or 0.15 of a second for that to change. You just won't notice. But you will notice if your video's jerky, or you will notice if you're on a Skype call and the sound goes weird. So they implement a quality of service, by which they mean if you are doing something that involves a particular service, like video, we will make sure that that has a certain transfer rate or a certain amount of data that will go through, so that it looks better or sounds better or doesn't become compromised. So that's one of the things the I/O system will do. It will schedule all that, but it also has to do all the buffering. So I said before that when I press a key or when I move the mouse, it interrupts and it says up, but it won't necessarily act on the up. It will only act on the up when my PowerPoint process gets some CPU time, and it gets some CPU time to realize that the mouse was talking to it and that I should move my pointer up. But in the meantime, the up command is going to sit somewhere, and where it sits is a buffer. So it's got some memory, so that it can keep that data. It's also got it because some devices are faster and some are slower. You might want to wait until you get a chunk of data from a disk. there's probably no point in sending over the first byte that you get from a disk. What's that going to do for you? You probably want to wait till you get the whole block. So it will buffer all that as well. When you do that, you start getting some issues in terms of which is the real copy. So I/O systems have to sort that out as well. So in essence, it smooths the path between data and where it's going, and vice versa. Part of the way it does that is remembering where things are. So it will keep a table for all your devices. And again, you've seen similar tables for other parts of the operating system. Here, it's about the devices that we have connected and whether they're busy or not. Device laser printer busy. If you know that that laser printer's busy, there's no point in sending out another job to it. In fact, not only is there no point, it would be very stupid to do so, because all you would do is mix up two data streams. So the I/O subsystem says, no, that's a laser printer. I know what a laser printer is, and it needs to finish what it's doing before I send it another job. So if I know it's busy now, I'm just going to keep this data, and then when it becomes not busy, I'll start work again. On the other hand, I might want to send multiple requests to a disk. And we saw that last week when we did different ways of accessing different data on the disk. And we looked at different ways that it could go about getting all those requests. It would be silly of it to not send other requests to the same hard disk unit, because actually you might be able to get some data while it's busy going to another part of the disk. So it actually understands these things and will decide what to do based on the type of device. And of course, it has to also understand that in terms of the speed of devices. And again, 10 years out of date, but the relative speeds are roughly the same. So a keyboard is slower than a mouse, which is slower than a modem that nobody uses anymore. This is a PCI hard disk, which is faster than FireWire. And if you don't know what FireWire is, it's now called Thunderbolt. Hardly anybody in a home setting would use SCSI, even in an office setting. But if you're running a server farm or something like that, you might still have SCSI connections. So you can see the different types of device and how fast they are. And the only thing that's changed here is, as with everything else, things get faster. Okay, so we have to take account of that. We have to understand that devices go at different speeds, and we have to account and make sure that that doesn't interfere with our operation. And one of the things we can do is keep copies of data to speed up or allow us to manage it. But there's different places that we would do that. So we have caching. We talked last week about it when we said that we might, if someone requests disk block 1, there's a fair chance that we'll want disk block 2. So let's go and get it, bring it into the cache, and then if they want it, we've got it there already. We have spooling. So if you have a printer and there's no point in sending more than one job at a time, you would store the next job and the next job and the next job in something called a spooler. And then when the first job's finished, the first print job's finished, you send the next print job and then the next print job, and that's held in a spooler. And we also sometimes allow exclusive access to a device. We reserve it to ensure that we can get to a certain performance level. If this wasn't a static screen, if this was video, it might decide that I'm not going to update the mouse quite so often. I'm going to reserve access to update the screen. Or I'm going to reserve access because I'm going to load a 4 GB video file and I want it all in before I start going to get other information. And again, it'll just depend on the operating system, the types of jobs that it has and the types of information that it goes through. It's entirely up to the operating system designer whether to build that in and in what circumstances you're allowed to do it. The other thing we're going to have to build in is error handling. What happens if something goes wrong? Hello, hard disk, send me a block. Oh, I'm having a problem. What do? Do you ask for it again? And if so, how many times? At which point do you say, no, I can't get that anymore? Again, that's a choice that has to be made. What if you've got multiple processes all trying to access I/O at once? Particularly if you're doing memory mapped I/O. What if two processes try and write to the same place at the same time? Well, maybe you want to stop that. Maybe you want to protect I/O. So instead of allowing the process to do it, you have to go through the operating system and say, no, you're not allowed to just write to memory. Tell me what you want and I'll write to memory when I'm good and ready. So instead of the program creating a system call, it actually says, no, let's go to the operating system, check what it is, make sure that I can cope with that. Only then will it be sent on to the I/O before finally being returned to the user. So the operating system will simply do what it does so many other times. It will get between you and making a mistake. And to do that, the kernel has to understand what kind of a devices it has, what sort of state that they're in. So as we've seen before, it will keep information on that. And it's going to keep lots of information on lots of different devices. So there will be different types of information. So it's not as simple as saying, oh, it's a block about, here's the file that's on a disk. The information that you want to store about a mouse will be different to the information that you want to store about a network, to the data that you want to store about a graphics card. There will be lots and lots of different data structures for all those different types of devices, all working in different ways. And you'll start to get things like this. Huge data structures talking about files that are open that point to file system records, which may also point to a networking record because your file is on a OneDrive, so you've got to go through a network to get to the file system and then understand what that's like. So it starts to become more and more complicated. And for any of you that were with me with the Introduction to Programming last year, this kind of says why closing the file once you've read from it is really important. Because otherwise the operating system can't open it again. It still thinks someone has access to it. You've opened it and says, I want this file. Please don't let anyone else use it. So if you forget to close it, you block off access to that file. Okay, so let's look in detail about how the I/O request actually happens. So the user requests some I/O, open thread.txt. You might already have that in a cache somewhere. You know, you've gone to open a file, you've gone to open some data, and you've brought in more than you needed, so it might already be in the cache. And it says, oh, okay, can we already satisfy it? And remember, the device won't know that, and that's another part of the reason for making this an operating system call rather than a device call. The operating system might say, Aha, I've got a trick up my sleeve. I already have this. Transfer it and go back to the user process. But if it hasn't, it has to say, okay, well, what do you want? Let's think about this. So it's on a particular device, so I need to go to the specific device driver for that device. That then needs to connect to the controller, which will process the request, ask for the data, and then bring it all back in, most likely to be stored in a buffer in the controller. So if you've got a disk, you might have a 1 to 4K buffer already in the controller. So once that block has gone back to the controller, it will then interrupt and say, oops, here's your data. That will generate the interrupt. CPU gets the interrupt, gets the data from the buffer, puts it somewhere in memory, figures out who it was that sent it that data and says, oh, okay, it was that request, so I can shut that one off and say that's done, and then go back to what it was doing. And then when the process that requested it comes back round, it can transfer the data and say, yes, IO is complete. So there's a lot of different systems and a lot of different steps here just to opening a text file. Which means, as ever, performance is going to be an issue. And you kind of know that. You know it takes a while to open a file. And you know it takes longer to get a file from a hard disk than it does from an SSD. And both of those are still faster than getting it from a network connection. So we have to think about performance and think about places where we can speed it up by using caches, by using buffers, by reading ahead, whatever it happens to be. All of those become multiplied when you're doing this over a network. So what you're doing is asking another computer to do something. You've got all the stuff that it would normally do, plus the overhead of one computer talking to another and getting that information. Because this bit here suddenly becomes connect to the OneDrive computer and let it do all this again, then let you know that it's got it before it does this. So in essence, you're doing it twice, plus transferring it over a network. So performance can get a hit. So there's lots of ways that we have, and we've spoken about some of them already, about how we can speed this up, whether it's DMA or caches or buffers or whatever. So that we end up where we are now. And every time we try and increase our performance, we can increase it anywhere. But of course, that's because every time we've done this abstraction and increased the abstraction, it increases the flexibility, but we also take longer to do it. So again, it's that balance, that trade-off that we seem to have been talking about for months. Yes, you could just go straight to the device, but that means that processes might overwrite each other, or you might bump into each other, and might be a problem. So you start to put some abstraction in, but that slows things down. But it means that you don't have huge crashes or whatever. So again, it's about getting the balance. And that's it. Anybody get any questions? No? Okay. If there's no questions, let me stop this recording.